Welcome to the next video lecture in the series of videos about lexical analysis. This one is LEX8, where we go into details about how we can use the finite state machines that we were using for recognition and pattern matching and combine them together to create a lexical analyzer. LEX6 and 7 go through in more detail to explain the subset construction, the conversion from an NFA to a DFA. And so this is actually going to explain to you how you can do the matching using the finite state machines. Once you know how to convert a regular expression into a finite state automata, then how do we sort of combine many different token definitions in order to do lexical analysis like we need to do in a compiler. Let's take an example to illustrate how this would work. So we have the first token definition is token A, and all it recognizes is a single symbol A. And the NFA for this would be this simple finite state automata here with start state 1, and then it accepts a symbol A and goes to a final state 2 over here. Token B is the concatenation of A, B, B. Finite state automata for that is then just the sequence A, B, B. You're transitioning from this start state all the way to this final state. And so this, at any point, if you're at state 4 and you get another symbol, it's just going to not be able to get to a final state, so it would reject that string. Token C is slightly more complex. It's A star B plus. So B plus means 1 or more B's, and A star means 0 or more A's. So if I was to write that down as a NFA, this is what it would look like. We have a start state here, and then we accepting 0 or more A's, and then on an input B, we can then accept as many other B's as you want. As long as you have at least one B, you can get to a final state, which is this state, 8. So let's say we have these 3 tokens and we want to build a lexical analyzer. We've already taken the regular expressions, right? And using the Thompson construction, we have converted them into these 1, 2, and 3, the 3 NFAs for those regular expressions. Now we want to recognize any strings either in token A, B, or C. So just create a new start state and link them up in the usual way using empty string transitions to the start states of each of the original ones. And this allows us to run all of the NFAs sort of in parallel, right? Because that's what the NFA lets us do. So for these 3 token definitions now, I can sort of check which path is going to lead to a final state. It's either the topmost path, the middle path, or the bottom path. Okay, so let's take the different token definitions. And as before, we're going to assume that there is an ordering here, so that token A is higher priority, token B is the next highest priority, and token C is the lowest. Let's understand how to do the matching for a lexical analyzer when you have a NFA by using this example. So let's say the input is AA, BA, and now we want to produce as output not just a matching for one match. So it's not like is this string accepted by any one of these tokens? Because what we want to do is match as far as we can and then start matching again, because in a program, there's not just going to be one token, right? You're going to have multiple tokens, one after the other. So once we've recognized the first token, then we're going to reset the matcher and then go from the next position after the first match and do the second match and so on until there's no more elements left in the input. Okay, so let's put some numbers here so that we can track where we are in the input string. So we have up to position 1 here, 2, 3, and 4. Okay, so when we start, think of it as NFA simulation or NFA recognition algorithm. So the start, we're starting from state 0, but because of the empty string transitions, we actually are starting from this set of states, right? We are starting from 0, 1, 3, and 7. Any state that you can reach from the start state on an empty string. So that's what this represents, is that set of states. And then the first input symbol here is an A, right? So we are starting from position 0 on input A. Where can I reach? Well, if I'm here at this position, I know that I can take a transition on A to reach 2. If I'm 3, I can take this transition to reach 4. And if I'm at 7, I can take this transition A and I'm back at 7. So I can reach 2, 4, and 7. And notice that of these 3 states, 2 is actually a final state. So this set of states is a valid final state. So I could stop here and return a token. And that token would be the first token here because that's corresponding to token A. So this is, we have reached basically this much of the string up to this point. And then we can go and accept the next input symbol A. And so we look at 2. From 2, there is no way to go anywhere. So we're stuck here. From 4, there is no way to go anywhere on an A. But if I'm at 7 and I see an A, then I can go back to 7, right? So that's why we have a set of states which only has one state in it, which is 7. Now the next symbol is a B. So far we've reached position 2, which is over here. And then the next input symbol is a B, and I'm at state 7, and I have an input symbol B. Then there is only one choice. I end up with this state 8. And notice that 8 is a final state, so I've marked it as a final state over here. And I've reached position 3 now, right? So I've reached up to here. Now we look at position 8 and we ask, what if I see an input A? Can I go anywhere? And the answer is there's nothing we can go to from 8. So at this point, we can look and see which token definition here got the longest match, if any. Right, so we did get one match over here, and we got one match over here. So token A matches from 0 to 1. Token C matches from 0 to 3. So the longest match is what we would pick. So token C is the winner. Now we are still not done, right? Because we have these 3 token definitions. The input we have read up to this point. So up to this point, we got token C. So now we restart from this position, and we start now again from the start set of states, so which is 0, 1, 3, and 7, and we ask what transition can we make on input symbol A, and we already know from before that there are 3 different transitions we can make on the input symbol A to state 2, 4, and 7. Now only state 2 of these 3 is a final state, right? And corresponds to this token A over here. And at this point, we have nothing else. So this just stands for there's nothing else in the input. So we are done with parsing the input string. And in this case, token A matches 3 to 4, and that's the only output we can match here. There's nothing else. So that is the longest match and the only match. So the output would be token C, which matches AAB, which goes from 0 to 3, and then this one is token which matches just a single symbol A, which is from 3 to 4. So what we've done is apply the finite state recognition algorithm, but what we've done here is apply it repeatedly so that we can match using the longest match algorithm, and we can also reset and match another token and so on. So each time we take the longest match. And as before, if there are 2 tokens that can match exactly the same sort of length of matching, then we pick the one that is a higher priority in this list. So token A is has a higher priority than token B, which is higher priority than token C. So the order in which they're defined matters. So when you're writing down a lexical analyzer using a finite state automata, so you could convert the NFA into a DFA, and the DFA then must find the longest leftmost match for a token, and we continue matching and we report the last final state that was reached once the DFA recognition algorithm or simulation is done. So basically can't go any further. And then we reset and go again. So the longest match means we keep matching all the way. We don't sort of stop halfway through just because there is another pattern that matches int as a reserved word. We match the entire print as a single matching. The leftmost match means that we're always going from left to right, right? So we start from here and we go one symbol at a time. So if I have a regular expression like a plus b, even though this is a longer match for a plus b, that doesn't matter because what we want is the longest match starting from the leftmost symbol. So what it will return is this one and not this one, obviously. So it can't skip over any tokens. And if two patterns match the same token, then pick the one that was listed earlier in this sequence, right? So you can think of it almost as the final states. If the final state of R2 is reached and the final state of R3 is reached, then we pick R2 over R3 as long as the matching is the same length. There are some advanced techniques in lexical analysis, like the look-ahead operator, and that's also pretty easy to implement. So if I have R1/R2, which means match R1 when followed by string in R2. So for example, if I have A star B plus, and the right context should have a star C, so it accepts the string, it takes this string BAC, and notice that it is A star B plus, so it doesn't need A's in the beginning as long as it has one or more B's. So it matches this B as a token, and this part over here, which is AC, matches this regular expression R2 over here. So AC is one A and a C, which is matched by A star C, and so in this case it would return B as a token because the context includes something that is matched by R2. But if I have an input like ABD, AB is matched by R1, but R2 is not matched for D because D does not belong to the language of A star C. So this one is ruled out and it doesn't do the matching for that. So the way to do this is to match R1 epsilon R2. So just create an NFA for the concatenation of R1 and R2, and you match up to a position Q in the input. So here's position P, and this would be position Q, right? So it matches all the way up to position Q, which is after the R2, but it remembers that position P, which was just for the R1 match. And then it gives you a token definition for R1, and then it resets and starts. The next start position will be P and not Q. So the next token definition will start reading the string after position P. So as an exercise for you, take a look at these token definitions. So there's token A, B, C, and D, and I've provided a sample input here. And what your job is to apply this lexical analysis algorithm. First, create the finite state machines for each of these, and then return the sequence of tokens. Creating the NFA is optional. It's good practice. But if you can figure out the sequence of tokens that will happen for this input, that's enough to check whether you understood the material. Be careful that there may be at some point no matches available, right? In which case it should return an error.